Swayam Prabha. Digital India. Educated India.
Good afternoon. In the last class, we were discussing about the check for bearing capacity failure. That is how you can find out the factor of safety against bearing capacity failure. In that respect, we found out that what will be the Q maximum and Q minimum at the base of the wall, that is base slab. So, let us try to see some of the points that you should take into account while you carry out further analysis in case of bearing capacity failure. You must always remember that summation V, which was there in that particular table, as I explained you in the last class, it includes the soil weight also. Now, we have found out the value of eccentricity. When this value of eccentricity becomes more than B by 6, in that case your Q minimum becomes negative, and as soon as that Q becomes negative, it indicates the development of tensile stress at the end of heel section. Q minimum is occurring at heel. If this Q minimum is negative, that gives the development of tensile stress. This stress is not at all desirable because the tensile strength of the soil is very small. So, we must avoid this kind of situation. So, in any case the eccentricity should not be greater than B by 6, where B is the width of base slab. Now, what happens if in the analysis, while analyzing the procedure, this E comes out to be more than B by 6? Then in that case the design should be reproportioned and calculation should be redone. So, let us say that you took a tentative proportioning of the wall, you carried out the analysis, it worked out to be safe against overturning, it worked out to be safe against sliding along the base, and then while you are working out the factor of safety against bearing capacity failure, and in that process if the eccentricity of the force comes out to be more than B by 6, immediately you should stop the analysis at that particular point of time and you should reproportion the whole thing and do the calculation altogether again, because development of any tensile stress is not at all desirable in case of soil. Then in the shallow foundation chapter, you already have studied that how you can find out the ultimate bearing capacity of the foundation, which is I am giving you for the reference purpose, that this way you can find out your QU. So, QU is equal to C2NC FCD FCI plus QNQ FQD FQI plus half gamma 2 B prime N gamma F gamma D F gamma I. Now, let us try to see what are the different terms in this particular expression. Q is gamma 2 into D, B prime is B minus 2E, E is the eccentricity that you have to obtain as explained earlier. FCD, FQD and F gamma D, they are the standard expressions given by Terzaghi or different other research workers. You can simply pick the standard values by using these expression for these. And FCI, FQI, F gamma I, they are the function of this angle psi, which can be obtained by this particular expression, that is tan inverse PA cos of alpha by summation of V. So, once the ultimate bearing capacity of the soil has been calculated, the factor of safety against bearing capacity failure can be obtained as factor of safety bearing capacity is equal to QU by Q max. So, this QU we are calculating using the expression either by given by Terzaghi or any other expression given by any other research worker, and then this Q max you have already found out. You remember that you found out that Q max and Q minimum. So, from there whatever is the maximum value of Q, you simply divide QU by that, and then you will be getting this factor of safety against bearing capacity. Generally, a factor of safety of 3 is required in this case, that is against bearing capacity failure. The ultimate bearing capacity of shallow foundations occur at a settlement of about 10% of foundation width. So, this aspect also we must take into account. Now, in case of retaining walls, the width B is large, and hence the ultimate load QU will occur at fairly large foundation settlement, and the factor of safety of 3 against bearing capacity failure may not ensure that the settlement will be within tolerable limit. So, this aspect we should always keep in our mind, and we should have the provision of further investigation as far as this aspect is concerned. As it is beyond the scope of this course, so I am not discussing all these things in detail, but you must always remember this thing, that although the wall is safe against the 3 aspects, that is overturning, sliding and bearing capacity failure. However, due to the large or excessive settlement, the serviceability criteria is not satisfied. So, in that condition we need to take the proper care. Now, this was all the theoretical part that we discussed. Now, let us try to take an example, so that will give you the feel that how you can find out the factor of safety against overturning, the factor of safety against sliding along the base of the wall, and the factor of safety against bearing capacity failure. So, we will take up an example. The cross section of a cantilever wall is shown in this figure below. Calculate the factors of safety with respect to overturning, sliding and bearing capacity. This is the statement of this example that I am going to solve here. You can see here that this is a wall, inclined backfill, which is having an inclination of 10 degree from the horizontal. This soil is frictionless, C1 is equal to 0. It is having angle of internal friction as 30 degree. The unit weight of this backfill soil is 18 kilonewton per meter cube. Here it is 20 degree and 40 kilonewton per meter square, C2 value. Gamma 2 value is 19 kilonewton per meter cube. That is, the soil which is lying below the base slab is having these properties. Then the soil is placed at a depth of 1.5 meter below the ground surface. The tentative dimension that has been taken here is that the thickness of the base slab is 0.7 meter. This height from this particular point, that is base of the wall, up to this much is 6 meters. Then here the part of this heel slab, that is the width of this heel slab is 2.6 meter. For this one it is like the thickness of the stem at the base is 0.7 meter, and this dimension is also 1.7 meter. Then since it is inclined, and we have seen that this active force will be acting parallel to this inclined face. So, you see this is the PA, that is the direction of this active force which is acting on the wall. It has been assumed that the failure is taking place along this vertical face. Its component, horizontal component is PH, vertical component is PV. Then this whole area has been divided, that is the weight of the soil is being represented by this area 4 and this by area 5. However, the weight of the wall is being divided into 3 sections, that is section 1, section 2, this small triangular area, and this section 3, which is the area of the base slab. Now, from this figure H prime, you remember that H prime was this total distance. So, that is equal to H1 plus H2 plus H3. where H1 is, you know, that is 2.6 the width of the heel slab, and that into tan of 10 degree plus 6 plus 0.7, and that works out to be 7.158 meters. Why we are finding out is that to estimate the active force you need to know this particular height, that is H prime. The Rankine active force per unit length of the wall, that is PA, is equal to half gamma 1 H prime square into Ka. If you remember that in the second lecture I gave you the standard table for the coefficient of lateral earth pressure. So, simply corresponding to phi 1 is equal to 30 degree and alpha is equal to 10 degree, you can pick this value of Ka simply by those standard tables. So, Ka works out to be 0.35. Thus, from this expression, if we substitute all the values, your Pa works out to be 161.4 kilonewton per meter. Then, vertical component of this particular active force is equal to Pa sine of 10 degree, that works out to be 28.03 kilonewton per meter. Similarly, horizontal component is Pa cos of 10 degree, which is equal to 158.95 kilonewton per meter. Now, after knowing these preliminary things, let us start that how we can find out the factor of safety against overturning. So, as I explained you while we were discussing the theory, we have to prepare one table which shows all the forces and the lever arm from the toe part of the wall or base slab. So, that table can be prepared, and you can see here the first column is dealing with the section number, second one is representing the area, third one is weight per unit length of the wall, then fourth one gives you the value of moment arm measured from the point C, and then moment about the point C. So, you see, if I take the first one, let us say this. So, what is the area? This is 6 meter multiplied by this. So, this is 6 into 0.5. 0.5 I have taken as the thickness of the stem. So, this area I know. Now, weight of the concrete, if you simply multiply this area by weight of the concrete, you will get this value. And then this is acting, you see, if it is, this is 0.5, so this is half of this is 0.75. Okay. So, then you add this distance to this 0.75, you will be getting 0.25, you will be getting the lever arm from this point C. So, that is 1.15. You simply multiply this weight per unit length of the wall by this moment arm, this will give you the moment about the point C due to the sectional area 1. Likewise, this sectional area 2, which is this small triangular part, you simply find out the area of this particular one, that is half 0.2 into 6, and then weight simply multiply by unit weight of the concrete in this area, and you will be getting this weight per unit length of the wall. Then the moment arm you can find out, it is 0.833 in this case. You multiply this weight per unit length of the wall by this moment arm, you will be getting this moment about C. Similarly, for the third one, see, this is 2.6 plus 0.7 plus 0.7, that is 4, multiply by 0.7, this will give you the area. You multiply by gamma of concrete, you will be getting weight per unit length of the wall due to this sectional area 3, and this will be acting at a distance of 2 meter. You see here, this moment arm is 2 meter. Simply multiply by those two values and you will be getting the moment about the point C. Likewise, you have the sectional area 4 and 5. You find out the area, multiply by the unit weight either of soil or of concrete, whatever the case may be, and then you can find out this moment about C by multiplying these weights to respective moment arm about the point C. In this problem, I have taken this gamma concrete to be equal to 23.58 kilonewton per meter cube. Then this PV we have found out that is the vertical component of active force, which worked out to be 28.03 kilonewton per meter, and this will be acting at a lever arm of equal to base width of the slab, which is 4 meter in our case. Multiply these two values and you will be getting here this moment about C due to this vertical component of active force. You simply add all the values, that is the value of weight of wall per unit length of the wall for section 1, 2, 3, 4 and 5, and then this particular PV you will result into this amount, that is 470.45 kilonewton per meter is the total vertical force which is acting on the wall due to the weight of wall, due to the weight of soil which is lying above the heel, and due to the vertical component of active force. And then you take the summation of all the moments that is in this particular column, that moment about the point C, that will result into 1128.98 kilonewton meter, that is the total resisting moment. Once this table is complete, now the rest part become little simpler for us. So you see here for all the 5 sections, that is 1, 2, 3, 4 and 5, we found out the weight by multiplying its area to respective unit weight of soil or concrete. Say for first, second and third section, we multiplied the area by gamma of concrete, that is unit weight of concrete, and we found out the weight per unit length of the wall. And then for 4 and 5, we multiply by this gamma 1, that is 18 kilonewton per meter cube, to the respective areas to get the weight per unit length of the wall. And then the overturning moment, as you know that the only overturning the only force which was causing the overturning was the horizontal component of that active force, which was PH, and that was acting at a distance of h prime by 3 from the base of the wall, and its magnitude we found out as 158.95. H prime we have already worked out, and this MO works out to be 379.25 kilonewton per meter. You have already found out summation MR. Here we calculated summation MO. So how we can find out your factor of safety against overturning is that the ratio of summation of all resisting moments to the summation of all the moments which are causing the overturning. So you see here 1128.98 divided by 379.25, which works out to be 2.98. And as I told you that for overturning the factor of safety can be considered between 2 to 3. So this is greater than 2. So the wall is safe against overturning. So the factor of, we have to find out, the objective was that we have to find out factor of safety against overturning, factor of safety against sliding, and factor of safety against bearing capacity failure. So here we have found out the first part, which is factor of safety against overturning, and it worked out to be 2.98, which is greater than 2, and hence the wall is safe against overturning. Now let us try to see that how we can find out the factor of safety against sliding. You know this expression, I have told you that how we came to arrive this particular expression, and I told you that the K1 and K2 value can vary between half to 2 by 3. So let us say for the considered problem, if I assume that K1 is equal to K2 is equal to 2 by 3, and your P will be half Kp gamma 2 d square plus 2 C2 square root of Kp d. This is standard expression for passive force, where Kp is tan square 45 plus 5 by 2, which is 20 degree in this case. So this works out to be 2.04, and d is equal to 1.5 as it is already given in the problem. So by putting all these values in the expression for passive force, we can calculate the magnitude of this passive force, and that worked out to be 215 kilonewton per meter. So factor of safety against sliding, use this expression. Summation V you already know because you have already prepared that particular table. K1, K2 you have already assumed. Phi 2 you know, C2 you know, PP you are calculating, PA cos alpha you have already calculated. So you simply put all these values in this expression, and then this worked out to be 2.73, which is greater than 1.5, so it is safe against sliding. So as I discussed that in case if it comes out to be less than 1.5, you need to provide a base key, but in this case it is coming out to be more than 1.5, so there is no need to provide any shear key or base key. Now let us try to see what is the third aspect, that how we can find out the factor of safety against bearing capacity failure. We know that before finding out that factor of safety, we need to find out Q max, that is one thing. Another thing is we need to find out the ultimate bearing capacity of the soil also, and for that first we need to find out the eccentricity of the resultant forces which are acting on the base of wall. So for that, eccentricity is equal to B by 2 minus summation Mr minus summation Mo divided by summation V. B is 4 in this case. All these three values we can pick simply from that particular table, and the eccentricity value worked out to be 0.406 meter. Now we have to check whether this value is greater than or less than B by 6, because if this eccentricity comes out to be more than B by 6, then there will be development of tensile stress, which is not at all desirable as the soil is very weak in tension. So here in this case B is 4 meters. So B by 6 is 0.666 meters, which is more than this eccentricity E. That means that there is no development of any tensile stress. So we can go ahead confidently for finding out the factor of safety against bearing capacity failure with the tentative proportions that we have assumed initially. So Q toe and heel we can find out here by this expression, that is summation V by B 1 plus minus 6 E by B. Summation V you can pick from that table. B is 4 meter in this case, 1 plus minus 6 into E we have right now found out, that is 0.406 divided by 4, and this equal to your Q toe value will be 189.2 kilonewton per meter square, and Q heel will be 45.99 kilonewton per meter square, which will be occurring at heel. Now this is what was the Q max that we have found out. So Q max value is 189.2 kilonewton per meter square. We need to find out Q ultimate also. So let us try to see how we can do that. So the ultimate capacity given by this standard equation, you know that for different values of phi you have standard tables. You can pick the shape factors accordingly, bearing capacity factors accordingly, which are NC, NQ and N gamma. So simply these values have been picked from the standard table. Q, which is coming here, is gamma 2 into D. Gamma 2 is 19 into 1.5, which works out to be 28.5 kilonewton per meter square. B prime is equal to B minus 2E. E you have found out as 0.406 meter. B is 4 meter. So that B prime works out to be 3.188 meter. Then FCD, FQD and F gamma D from standard expressions. Similarly, FCI, FQI you require psi degree, and that psi degree is defined as tan inverse PA cos alpha by summation V. PA cos alpha you know, summation V also you know. You can simply pick these values from the table. That psi degree will become equal to 18.67 degree. Once this psi is known, you can find out this FCI and FQI. So FCI and FQI they worked out to be 0.628. However, F gamma I, which is equal to 1 minus psi degree by phi degree whole square, that is approximately very less value. So I am taking approximately that to be equal to 0. So Q will become Similarly, you have the expression, simply put all the values in that expression and then this Q value will work out to be 574.07 kilonewton per meter square. Please note it that since this f gamma I worked out to be 0, that is why this third term is coming out to be 0. If it has some value, you simply put that value and then you get the corresponding value of Q. Then factor of safety against bearing capacity failure, it is equal to Qu by Q max. Q max in this case is equal to Q toe, that you have already worked out, and this works out to be 3.03, which is greater than 3. So, the wall is safe against bearing capacity failure also. So, I hope the procedure of obtaining the factor of safety against overturning, the factor of safety against sliding along the base, the factor of safety against bearing capacity failure is clear to you, that how you can implement all the theoretical things as we discussed into any practical problem. Now, this was all about the stability of the wall. There are few points or comments that we must know about the stability of the walls. So, let us try to discuss one by one that what are those comments related to the stability. So, when the weak soil layer is located at the shallow depth, that is within a depth about 1.5 times the width of retaining wall, the bearing capacity of the weak layer should be carefully investigated. As you know that wherever there is a presence of any weak soil layer, we need to be extra careful. So, that is what this first comment tells us, that we need to be extra careful for the bearing capacity of weak layer. Then we have not talked of anything related to the settlement, but that is an important serviceability criteria you must always keep into mind, that the possibility of excessive settlement also should be considered. It may happen that the wall is safe against overturning, sliding and bearing capacity failure. However, the settlement can be quite high. So, for that possibility we should always keep into our mind. The use of lightweight backfill material behind the wall may solve stability problem. So, that also is another option. Then piles are used to transmit foundation load to the firmer layer. You will be studying these piles, just for the time being you can think of that during your foundation chapter you have studied for shallow foundation. Piles are kind of deep foundations. We will be discussing them in subsequent lectures, but for the time being you just simply think that it is a kind of deep foundation. However, often the thrust of the sliding wedge of the soil in case of deep shear failure bends the pile and eventually causes them to fail. So, we need to keep into account that when the piles are being used, that they should not bend and should not fail. So, careful attention should be given to this possibility when considering the option of pile foundation for retaining walls. Then, the active earth pressure coefficient is used to determine the lateral force of the backfill. The active state of backfill can be established only if wall yields sufficiently, which does not happen in all the cases. This aspect we have already discussed, that for any soil to enter into either active state or passive state, the wall must move or must yield sufficiently so that those conditions are generated. So, usually in all the cases it is not generated. So, we must take into account that whether the active condition or the passive condition is really getting generated or not. The degree of wall yielding will depend on its height and the sectional modulus. Then furthermore, lateral force of backfill depends on several other factors. What are those factors? See, we have simply taken the property of backfill material into the analysis. We have taken the property of the soil which is lying below the base slab into the analysis, but there are some of the factors which we have not accounted for in the analysis, and these factors, although we are not taking them into analysis, but you should have little idea that there are factors which influence the stability in this aspect also. They are effect of temperature, then groundwater fluctuation. See, we have not at all talked of any presence of groundwater table. Here we are talking of groundwater fluctuation. So, how we can take into account this groundwater table, that we will be discussing little later. Then readjustment of soil particles due to creep and prolonged rainfall, then tidal changes, heavy wave action, traffic vibration and earthquake also. Then insufficient wall yielding, when combined with other unforeseen factors, it may generate larger lateral force on retaining structures compared to that obtained from the active earth pressure theory. See, you are finding out the active force from various available active earth pressure theories. Out of them, we have discussed two within the periphery of this course, within the scope of this course. One was Rankin's theory, another was Coulomb's theory. So, what happens is, since the wall is not yielding to give you exactly the active or passive condition generated, and along with those you have seen that there are many factors like groundwater fluctuation, temperature, earthquake, etc. They cause the larger active force which we have obtained from the available theories. So, how we can take into account that kind of situation, because in reality the wall is subjected to more lateral force as we are calculating from these theories. Difference in actual and theoretical pressure distribution can occur due to various things, that is, the actual lateral earth pressure distribution may not be triangular, it can be, it depends on the type of the soil or any other thing. This is what we have assumed, that it is failing along the triangular wedge, it may not be triangular. Then second one is the lateral earth pressure distribution may change with time, that maybe today it is this, then after 2 months it may be something different. The actual active force is greater than that the minimal theoretical active force which we are calculating from the available theories. The primary reason that many retaining wall designed with theoretical active earth pressure they perform satisfactorily is the use of large factor of safety. See, we took factor of safety to be equal to 2 to 3 for overturning, 1.5 for sliding and then 3 for bearing capacity failure. They are towards higher side. So, they take into account all these uncertainty, that is if the actual active force is different from the theoretical active force. See, I was telling you that in the analysis of the retaining wall, we are not considering any pore water pressure which is getting generated, maybe due to presence of groundwater table or any other source of water. Usually in the analysis we do not take into account all these things. However, the drainage conditions or the proper design of the drainage is being done in case of retaining wall, so that there is no development of any kind of pore water pressure. So, let us try to discuss some of the aspects of these drainage, that let us say in case if there is rise in water table, then pore water pressure will get generated, and if the proper drainage facility is available over there, this will get drained out and then there will not be any development of pore water pressure. So, let us try to see that what are the various aspects of this drainage and how you can facilitate this drainage in the backfill part. As a result of rainfall or other wet conditions, the backfill material for retaining wall may become saturated. This saturation will increase the pressure on the wall and may create an unstable condition, because you see we have not taken any pore water pressure into account while designing the wall. So, in case if the water is present, additional pressure will be developed, and in that case the wall is not designed for that additional pressure. So, that is why there will be chances of failing the wall. So, there should not be any development of pore water pressure. So, for this reason adequate drainage must be provided by means of weep holes or and perforated drainage pipes. You can either use weep holes or you can use perforated drainage pipes or a combination of both. This is how it looks like. You see here, this is kind of backfill. This is another side, the ground surface wall. On this side of the wall, that is towards the backfill side, there is provided this filter material. This is the filter material, and then the weep hole is being provided. So, whatever is the thing is, the pressure is coming from this side, from this soil to the wall. So, whatever water is coming or getting generated, the pore water pressure which is getting generated due to any reason, that particular water, it comes to this filter material and it goes out through this weep hole and it is drained out. Okay. Then what should be this filter material? That we really have to be cautious that the soil particle which are the part of this backfill, they should not clog this filter material, otherwise its functioning will be hampered and all other things. So, there are various provisions that we must take into account. We will be discussing one by one them, but here it gives you the pictorial view that how this arrangement is being made. What do you understand by weep hole? Where the filter material is provided. So, you see filter material is provided towards the backfill side. The water, whatever be the reason for which it is present, it can get passed through this filter material and through weep hole it can just drain out from the backfill soil. So, these are drainage provision for backfill of a retaining wall. Then weep holes, if provided, should have a minimum diameter of about 0.1 meter and be adequately placed. You see, if it is having lesser diameter, what will happen, that it may happen that many a times the soil particles from backfill, they are also coming with water and they may clog the weep hole, which will result the insufficient drainage and will cause the wall to become unstable. There is always a possibility that the backfill material may be washed into weep holes or drainage pipes and ultimately clog them. Thus, a filter material needs to be placed behind the weep holes or around the drainage pipes. You see, if your let us say the water is getting accumulated here, it has to pass through this weep hole. If this filter material is not here, what will happen, that some of the clay particles or some of the soil particles will come with the water, they will come through this weep hole and simply some of them will pass through that weep hole and some of them will be remaining, and over a period of time they will clog this weep hole. So, that is why this filter material is provided over here, so that the first filtering of the water from this backfill material takes place at this particular stage only. So, many of the soil particles, they get stuck up here, they get filtered out here, and then only water goes into this weep hole. So, that is what is that, the filter material is placed for that particular reason. Geotextile may serve the purpose of filter material. Whenever granular soil is used as filter, there are few principles which should be followed. You see, if there are various type of geotextiles which are present over there, or you can say that various type of geosynthetics are there, they have 5 type of function. One is separation, reinforcement, then filtering, they work as membrane and all other things. So, if you can provide for that any particular kind of, that is filter kind of function of that geosynthetic, it serves very nicely, but in case they are little bit costly. So, usually let us say that if any granular material is available at the site, that is also can be used as filter material. But to use whether that particular material is suitable as filter material or not, for that there are few guidelines which you need to have a check on. So, what are they? Let us try to have a look on all those criteria. There are mainly two factors which influence the choice of any filter material in case of granular fill. See, now I am talking of this filter criteria with respect to granular fill. In case if you are using this granular fill as the filter material, then only this filter criteria you need to keep in mind. First is that is the grain size distribution of filter material should be such that the soil to be protected is not washed into the filter, that is the soil which is getting mixed with water, it should remain in the backfill region only. Then excessive hydrostatic pressure head is not created in the soil that has lower coefficient of permeability. So, that also you must take into account. So, to satisfy these two criteria, research workers have given some of the guidelines, that if those guidelines are satisfied, then you can use those particular kind of granular material as filter. So, the preceding conditions can be satisfied if the following requirements are met. This is as per Terzaghi and Peck, which they gave in 1967. So, first condition was that soil to be protected is not washed into the filter. Second is excessive hydrostatic pressure head should not be developed. So, in case if this D15 of F stands for filter, B stands for backfill material. D15 of filter divided by D15 of B should be less than 5. If this condition is getting satisfied, that means that the soil which is to be protected is not getting washed into the filter. If D15 of filter divided by D15 of backfill material, if it is greater than 4, it satisfies the second condition, that is the excessive hydrostatic pressure is not developed into the soil. Now, in these relations, as I told you that the subscript F and B refer to the filter and the base material. Base material means the soil which is to be protected, that is the backfill soil. D15 and D85 they refer to the diameters through which 15% and 85% of the soil will pass, that is in case of filter or the soil as the case may be. Then the US Department of Navy in 1971 they provides some additional requirement for filter design to satisfy condition 1, that is the soil which is to be protected should not get washed into the filter. What are those conditions? There are two conditions which have to be simultaneously get satisfied, that is D50 of filter divided by D50 of base material, that is backfill material, should be less than 25, and D15 of filter and D15 of base material or backfill, it should be less than 20. Now, these were the criteria. Let us try to see with the help of an example that how you can use such guidelines to suggest whether this particular material is suitable as filter material or not. So, here I take one problem, that the figure shows the grain size distribution of a backfill material, determine the range of grain size distribution of the filter material. So, you see here this is the grain size which is in millimeter, this is percentage finer, this is the grain size distribution of backfill material. This is D15 of B, B stands for backfill material, D50 of B and then D85 of B. Now, let us see. So, from the grain size distribution we can find out D15B, that is you simply go here, pick the value 15, pick this value, read here correspondingly, and that will give you this 0.04 mm. You see here this is on log scale. So, you simply go to 15, pick this, take here this value, and this corresponds to 0.4 mm. Similarly, you can find out D50, that is here, you see this is 40, this is 60, you take this 50 value here, go down here and then read this corresponding value which is 0.13 in this case, and then D85B is 0.25 mm. Now conditions for filter, as just now we discussed, that D15 of filter should be less than 5 times D85 of backfill material, which is equal to 0.25. We have found out from the given grain size distribution curve of backfill, that is 5 into 0.25, which is 1.25 mm. Then condition for filter, the second condition was D15 of filter should be greater than 4 times D15 of backfill material. D15 of backfill material is 0.04 mm. So here this is 4 into 0.04 mm. So that results out to be 0.16 mm. Third one was that D50F should be less than 25 D50 of the backfill material, that is 25 into 0.13. 0.13, see, we have found out here 0.13 is D50 backfill material, it is given in the problem. That works out to be 3.25 mm. Fourth condition was that D15 filter, it should be less than 20 times the D15 of backfill material. Now what is D15 of backfill material is 0.04 mm. So that will be 20 into 0.04, which is 0.8 mm. So you have seen that Terzaghi and Peck gave two conditions to satisfy the conditions given, as that the soil should not pass through the filter material, and then the second one was that additional hydrostatic pressure or extra hydrostatic pressure should not get developed in the soil. However, the Department of Navy in US in 1971, they gave additional two criteria. These are the additional two criteria. So all these criteria have to be satisfied simultaneously, and if you follow this one, you see 4 criteria, that D15F should be less than 1.25 mm, D15F should be greater than 0.16 mm. So the range of D15F is between 1.25 and 0.16. So D15F should be lying in between 0.16 to 1.25 mm. Then D15F, it should be less than this 0.8 mm also. So you see here, by taking into account all the 4 conditions, that is, you see 4 times D15 for backfill, 5 times D85 of B, 25 times D15 of B, and then 25 times D50 of B. You have the limiting 2 curves. You see, one is this, another is this. So this is the range in which you can choose any filter material. So you take any filter material, get the grain size distribution of that particular material. If that grain size distribution fall in between this particular area, then you can go ahead or you can choose that filter material to protect that or to use that particular material as the filter material. So this way it gives you the range. See, there is no hard and fast thing that this should be the exact property for any filter material. It usually provides you the rough range. So once you know the upper limit, once you know the lower limit, if you have any material, let us say somebody comes to me, he says that I want to provide a check whether this material is good or appropriate for using as filter material or not for this type of backfill material. So that consultant provides me the grain size distribution of backfill material. I have these 4 criteria. I can find out that what is the upper limit and what is the lower limit. Now he has given me the material which I have to test whether it is suitable for filter material or not. From the sieve analysis and other things, we can find out the grain size distribution of that filter material. If and then along with that, we know this upper limit and lower limit also we can find out. Now if that grain size distribution falls in between this range, I can simply recommend that particular consultant, you see this is lying in between this particular range, so you can go ahead or you can adopt this particular material as filter material to protect this backfill material. So, this is the way you can find out. Now, you see these limiting points have been shown in figure. Through these points, two curves can be drawn that are similar in nature to grain size distribution of backfill material. See, one thing you should keep into mind, that you see here, this this is kind of S-shaped curve. Okay. I can join, I just have 2 points here and then 2 limiting points here. I can join these 2 points simply by straight line. I can join these 2 points like this. I can join these 2 points like this. Any manner. I have infinite number of manners that I can join these 2 points. But what we keep into mind, that whatever is the shape of grain size distribution of this backfill material, one must try to follow exactly that the same grain size distribution. You see that here this has been plotted approximately in the similar manner as the grain size distribution of this backfill material is, right. So, you do not have to do like this or any other kind of thing. Simply follow the pattern which this backfill material's grain size distribution is following, and you get these 2 curves. So, through these points, 2 curves can be drawn that are similar in nature to grain size distribution of backfill material. These curves define the range for the filter material to be used. Okay. So, this is what was about the filter design criteria. So, we were discussing so many aspects of this lateral earth pressure theories and retaining wall. Earlier, we studied that what are the various lateral earth pressure theories, how this lateral pressure gets generated on any kind of structure. If you have to widen any road, then how this comes into picture. And then after that, we saw that how important it is that proper estimation of this lateral force should be done. After that, we saw that there are few theories that this lateral earth pressure can be estimated properly. The 2 were Rankine one and the Coulomb's one. Then similarly, we saw that either the wall can be at rest, it can move towards the soil, it can move away from the soil. If it is moving away from the soil, it creates your passive condition, and in that case you need to estimate the passive force also. And then after that, subsequently, when we estimated that, we found out a way to estimate the lateral earth pressure. Then we saw what are the various types of retaining walls and all the things. Then we found out that how we can proportion the retaining wall, be it gravity retaining wall or be it cantilever retaining wall. And then we saw that after proportioning, how you can provide the check for the stability, that is how you can find out the factor of safety against overturning, against sliding of the wall, and then against bearing capacity of the wall. While designing and analyzing retaining walls, we did not even see that what are the let us say if any water table is present over there, we did not take into account that, and that is why we need to go for proper drainage measures. And that is how we saw that what can be the proper drainage measures that we can take into account while we provide the retaining wall at the site. For that, if you can use geosynthetic as filter material, you can use any granular material as filter material. In case if you use any granular material as filter material, you need to follow some of the criteria, some of the guidelines which have been provided by the earlier studies, and that is how we saw that there are 4 conditions. And then with the help of an example, we saw that how we can incorporate these to find out whether any particular material is suitable for filter material or not. Thank you.